Hi everyone, we are continuing with what we've been doing with Taylor polynomials and Taylor series, except we're moving on to error. And this is specifically what we call the Lagrange form of error. And so just a few vocabulary things first of all, just to get the main idea. All right, so a partial sum is the sum of the first however many terms of the series. Okay, it's not the whole thing, it's just a part of it. So the partial sum. Okay, the tail is what we call the rest of the terms. Okay, and the remainder is the sum of the rest of the terms. Right, so kind of obviously the error is the sum of the rest of the terms. Okay, so if we get a partial sum, that's going to be an estimation, okay, and the error of that estimation is going to be the remaining terms. Right, it's kind of intuitive, but still it needs to be said. Okay, so our error is going to be the same thing as the remainder. So a lot of times you're going to see that represented with a big R. Okay, for alternating series, okay, which you do have to show the three convergence things, the absolute value of the first term is like our error bound. It's the maximum value of our error, which we did before. And then if you can do the integral test, that'll also give you the error bound, which is something that we also did before. Okay, what is interesting about the Lagrange remainder or error bound is that essentially, if you look at this, okay, so if this is our partial sum right here, our error bound is denoted with this notation, and it should look pretty similar. It is our next term, right? So it's the n plus 1th term. It's the next term. If we stop at n, then the next term is our error or our remainder. Now, specifically with this case, what's to note is that we have a z here, not an x or not a c or whatever else. Okay, it's a z. It's a totally different number. Okay, and what that means is that between your center and whatever value of x that you're evaluating the function, there is some value of z that gives you the perfect remainder. It's very similar to mean value theorem in that case. Okay, there is some number in between your center c and the value of x, which we're going to call z, that gives you the perfect error or a perfect remainder, essentially. Okay, and you're going to plug that into your next term, the n plus 1th term, and that gives you an error bound. Right, so the great thing is that what we can do is just plug in our maximum, okay, the biggest that number could be. We usually don't have to find z. Sometimes it's very difficult to find z, but a lot of times we'll be able to get a maximum value for f whatever derivative of z. Okay, and sometimes the problem will be that most of the time that'll be given to you. So that's what makes it a little easier. Now, there was a 2011 BC problem that you can look up that asks pretty much the same question. Okay, it's very common to see absolute value p minus f or f minus p. Okay, this is really asking you to find the error. Okay, this is just a fancy way of saying find the error, find the estimation minus the actual value, but in absolute value bars order doesn't matter. So just find the difference between your estimate and your actual value. That is your error. Okay, and the way that they did that was by finding our Lagrange remainder. All right, so let's talk about how to actually do that. All right, so here's what we're given. Okay, we're given some values, and we're asked to write a third-degree Taylor polynomial about x equals 2. So we're centered at x equals 2. This is our center. I'm going to write that a lot better. This is our center, and we're going to try to approximate f of 2.3. Right, so I'm writing my third degree. So my first is my constant, and then 4. I'm centered at 2, so I'm going to write x minus 2 here. Minus 7 over 2, x minus 2 squared, and then 8 over 3 factorial, x minus 2 cubed. And you could write a 2 factorial here if you wanted to, and you don't have to. 2 factorial is just 2. So this is our third degree Taylor polynomial. I'm using this to approximate f of 2.3. Okay, so that's going to be approximately p sub 3 of 2.3, which is, if you plug 2.3 in, you'll end up getting 6.921 if we truncate after 3. Okay, now the fourth derivative has a maximum value. The absolute value of my fourth derivative has a maximum value of 9. Okay, no matter what number you plug into my fourth derivative, the maximum value is 9, between 2 and 2.3. That's important because this is my center. This is the value that I am approximating. Right, now I'm trying to find a bound for the error of my approximation. Well, I know that my error, it has to be less than or equal to the maximum value between 2 and 2.3 of f to the fourth derivative of x, right? And divided by 4 factorial times 2.3 minus 2 to the fourth power. Right, so all I did was I wrote out my next term, okay? Fourth derivative, 4 factorial, fourth degree, and I plugged 2.3 in for x, which is what I did right here. Okay, I plugged 2.3 in for x. All right, the nice thing is that they told me what my maximum value is. They said it's 9. Okay, they said my max value is 9. So I have 9 over 4 factorial times 0.3 to the fourth power, which is a very small number. Okay, very, very small number, so pretty good error bound. And now keep in mind, this is not my actual error. This is the biggest that my error could be. My error is less than or equal to this. Right, or actually, well, error is inherently positive, but like the absolute value. Okay. So then they're asking me to use this to bound my estimation. Right, so I know that f of 2.3 has to be between my estimate, which is 6.921, plus my maximum error, and it has to be greater than my my estimate minus my error bound. Okay, so that gives us an interval of 6.917 and 6.924. All right, so a difference of 0.007. Okay, so this is my similar to like our interval of convergence. Okay, so that is where my value is going to be. It's going to be definitely between those two numbers. Okay, and it could equal one of those two numbers. Okay, now it's asking if I could equal 6.922. Well, that does fall in my interval, so yes, it could. Could it equal 6.927? That falls outside of my upper bound, so no, it could not. Right, and for explanation, just look at the inequality that I just did. All right, let's do another one, this time with sine, because we like trig. Okay, we want to find a third degree Taylor polynomial about x equals 0. Yeah, at least they did that. So I got to write out some things. Okay, I need to establish all of my derivatives up to the third derivative. So f of x is sine of 5x plus pi over 3. Okay, f prime is going to be 5 cosine of 5x plus pi over 3. Double prime is going to be negative 25 sine of 5x plus pi over 3. Right, and then our third derivative, which I kind of ran out of room, is going to be negative 125 cosine of 5x plus pi over 3. Okay, so I established my three derivatives here, and I have to plug in 0. Right, so I need to find f of 0, which is root 3 over 2. Okay, f prime of 0 is 5 halves. F double prime of 0 is negative 25 root 3 over 2. And f to the third prime of 0 is negative 125 over 2. Okay, so using this, I can write out my third degree Taylor polynomial. So p sub 3, all right. They wrote p of x, you could write p of x. I like having that subscript. So that is my constant plus my first derivative times x. You know, it's x minus 0 because this is Maclaurin. Minus 25 root 3 over 2 divided by 2 factorial x squared minus 125 over 2 over 3 factorial x cubed. All right, so this is my third degree Taylor polynomial. Now they're asking me to use the Lagrange error bound to show that my error, remember this is just a fancy way of saying error, is less than 1 over 1200. Okay, well, I need to figure out what my fourth derivative is. So that's going to be 625 sine of 5x plus pi over 3. Do not forget to do chain rule when you're doing these derivatives. Okay, well, I need to establish what the maximum value is between 0 and 1/15th, because that's the value that they're asking me to estimate. Okay, I'm centered at 0, that's where the 0 comes from. The 1/15th comes from what I am estimating. Okay, so that's right here. Well, the maximum value of sine is 1. Right? So like basic parent graph of sine has to be between 1 and -1. Think about your unit circle. It has a radius of 1. Okay, there's no value of sine that's greater than 1. Right, nothing you can plug in that'll give you a value greater than 1 if you plug it in the sine of x. So this is my bound essentially. Right, so the biggest that sine of whatever could be is 1. So if I substitute 1 in for sine, because that's my maximum value, then this would be, I would just get 625. Okay, so my maximum is 625. Okay, because again, the biggest sine could ever be is 1. So if sine is 1, sine of whatever is 1, then 1 times 625 is 625. Okay, so that's the maximum that my fourth derivative could ever be. That's the biggest value that I could achieve. I don't really have to verify that it's between 0 and 1/15th. This is just the biggest that it could be, so I'm just going to go with it. Okay, so I know that my error has to be less than or equal to my maximum value, which is 625, and then my function. So this is what I'm plugging in for x, so x minus 0 to the 4th power over 4 factorial. Right, now just a little bit, let's just break this down and do this in our heads. So this is 625 over 15 to the 4th power times 4 factorial. Right, well, 625 is the same thing as 5 to the 4th. 15 to the 4th is the same thing as 3 to the 4th times 5 to the 4th. Right, so we cross those out, which leaves us with, you plug this in your calculator at this point, or just go ahead and calculate it out, because this is 81. This is 24. You end up getting 1 over 1944, which is indeed less than 1200. So we're good. Okay, we did show that our error was less than 1200. All right, that's it. See y'all later.